Alright, this is what you're looking at. So this is a block diagram. Okay, and if you look at this block diagram, you will, and your goal is, let's say, to find the equivalent transfer function or the equivalent block diagram. One, what you can do is you can reduce this block diagram using the three forms: cascade, parallel, and feedback form. Or what you can do is you can represent this using signal flow graphs and use Mason's rule. We have looked at how to do block diagram reduction. Let's look at how to first convert this into signal flow graph and use Mason's rule. Okay. So you have this. We have 1, 2, 3, 4, 5, 6, 7. So how many signals do you see? You see 1. This is a signal. 2, 3, 4, 5, 6, 7. And then you have 1, 2, 3. And that's what I did first. So signals is 1, 2, 3, 4, 5, 6, 7, and 8, 9, 10. Okay? And how many systems do you see? So you have 1, 2, 3, 4, 5, and 6. Now, whenever you need a system, but you don't have something to represent, you'll use 1. Okay? So this is R of S. And then you have V1 of S, V2 of S, V3 of S, right? V1, V2, V3, V4, okay. V4, V5, and then you have C of S. And this is V6, V7, V6, V7, V8. And then we'll identify the systems using another color. We have between V1 and V2 you have G1 of S. Between V3 and V4 you have G2 of S. And between E5 and CS you have G3 of S. Okay. So the rest are you can just say the rest are 1. Okay. And you have this and this. So here this is H3 of S, and this is just 1. And do you see a negative sign? So this you can say is -1. Okay. And another feedback is from here. Which one? It's loop. It's not straight line. It's like this. It doesn't matter really. You can draw a straight line, it will still be the same. But this is the practice. Okay. We have H2 of S. And then you have finally this is H. This is minus. Okay. And there's one more, which is from V3 to V4. So you have V3 to V4. Let's do this. Okay. This is a forward path. Okay, this is again, this is +1. Okay. So this is what you need to do as part of your first step. Okay. So given a block diagram, you need to come up with your signal flow graph. Now you can just switch on the lamp. The second, then we start looking at various definitions and identifying components according to those definitions. Yes.
So you put your V, I guess put it your V or V6. Your -1, like you put it into V1. So pick up summation point, I guess joint point. That's exactly what it's called.
Say that again. V. Summation blocks. Just do this. There are no summation blocks in signal flow graphs. So you just use this. Okay. So you have when we now we start looking at definitions. Then the first definition is you look at loop gains. Okay. Loop gains. Instead of looking at the definition, I'll just tell you how to figure out loop gains. Okay. So you start at each of these signals. Okay. You don't have to look at that one now. You understand the first step, right? If you start here, do you see a loop going from this to this? No loop, right? Do you see a loop from this to this? But do you see a loop from, you see there is a loop going this way, right? So the loop gain here is, the first loop gain is G1 of S, G2 of S, and H1 of S. Okay? G1, G2, H1. We don't include the signals here. Got it? These we don't include the signals. V2, V1, loop. The negative sign will be a part of it. All right? You can, if you want, you can reduce this further. See, this V6 signal doesn't have much of a value, so to say. Okay, if I just took it off, nothing would change, but we'll just keep it. So this is the first loop gain. Can you identify any more loop gains? So you go from, now do you see a loop gain here? So what is the loop gain here? It is negative G2 into H2. H2 is actually this, it corresponds to this, right? So it's this H2. That system. Okay. Do you see any other loop gain? You don't see loop here, loop gain, no loop gain here. You see a loop gain here, right? So the third one is negative G3 of S to H3 of S. Where? This one? No, that is not a loop, because this, you see this direction? Right, it has to, the direction has to follow, right? So this is not a loop, because if you look at the direction, it's different. The signal is going in that direction, okay? So the only three loops or loop gains you're going to find are this one, and this one. Now, if you had, actually there is one more loop gain, okay? It is G1, this, and this. You see it? Now that makes a loop. So G1, 1, 1, H1.
Going from like where V3 is, up around, coming down.
V3, this one?
And coming down to where H2 is.
That is another loop, yes. Right. Good, Sammy. So you have minus G1 into H1, right? So this, now you skip G2, correct? Because you're going this way. So it's just minus G1, and you don't see any negative signs here, right? There's minus G1, H1. And the final one is minus H1, H2, okay. So you have this. This is the first loop. This is the second loop. This is the third loop. And you have, this is the fourth loop. And then you have fifth loop. Okay. And these loops have to start and end at the same signal. Okay. So this is first step. Okay. The second one is forward path gains. Okay. So starting from the input signal to the output signal, you have to look at the forward paths, number of forward path gains. So there are, if you look at here, there is 1 G1, 1 G2, 1 G3. That is the first forward path. You see it? From input to output. The other is you see it? Now, there are two forward path gains. The first one is G1, G2 and G3, and the second one is G1 and G3. Okay. And now you have the third one is non-touching loop gains. Okay. So what you do is, for non-touching loop gains, you take these and you figure out, so how many combinations, these are the loop gains, right? How many combinations are you going to get out of these loop gains? How many combinations of are you going to get taken two at a time? You understand? You recall probability a little bit? So you have, see, the number of combinations taken two at a time is 2C2, 2C5, right? Because this is not, you don't consider permutation because the order does not matter. So this is 2 factorial, or this is not 2C5, 5C2. 5C2, which is 5 factorial over 5 minus 2 factorial into 2 factorial, which is 5, 4, 3, 2, 1 over 3, 2, 1. So this goes into 2 factorial is 2. So 2, 2. You have 10 combinations of taken 2 at a time. So the 10 combinations would be, so how do you get 10 combinations? 1, 1, 2, 3, 4, 1, 2, 1, 3, 1, 4, 1, 5, 4 combinations, 5, 6, 7, that is 7, 8, 9, 10. You see what I did? Combined 1 with 2, 3, 4, you get 4 combinations. Combine 3, 2 with 3, 4, 5, you get 3 combinations. You do it with 2, 1, 2, and then you do it 1. No, it works no other way. That is the only way it's going to work. Because these are combinations. If it were permutations, it would just be twice this. This would miss. Permutation is you consider the order. You don't consider the order. So 1 and 2, 2 and 1 are different permutations. Okay. So you have 5C2. How many combinations are you going to get if you take 3 at a time? You're going to get 5 factorial over 5 minus 3 factorial into 3 factorial. So this would be 5, 4, 3, 2, 1 over 2 factorial into 3 factorial. So this would still be the same. Okay? So this will still be 10 combinations, and finally 5C4 would be 5 factorial, this would be 5, and 5C5 would be 1. So when you're talking about non-touching loop gains, you have to take into considerations all these combinations. Okay? For assignment, for exam, you're not going to get anything this complicated. Okay, you'll get a much simpler problem. So you have, if you take 2 loops at a time, if you take these 2 loops, are these 2 loops touching each other? So this is a simple way of looking at it. If there's common gain, then they are touching. Okay? So G2 is common, right? So they are touching. That means they are touching. Are these 2 touching? 1 and 3? So 1 and 3 are not touching because you don't see any common gain here. Do you see a common gain? Huh? So let's look at the loop itself. G1, G2, H1, G1, G2, H1, and G3, H3. So these are non-touching loops. This is the first non-touching loop. So what you're going to get here is G1, G2, H1, and G3, H3. Okay. Now if you take this one and this one, they're touching, right? Because you have G1 and this, and then you have this. So this is common. So those 2 loops are touching. And then you take this one and this one. Again, here they are touching. You have G1, G2, and then you have this. So this is common. If you take 1 and 5, G1, G2, H1, G1, G2, H1 is this loop. And then you have this one, right? Those 2 are touching because you see this is common. Loops are touching. Okay. So forget about the common gain. Just look at loops and see if they are touching. And that is what you need to figure out. You have to figure out non-touching loop gains taken 2 at a time. Right? Yes.
So what if are common or touching because they have a common signal?
Right. Because they have a common signal, or they are simply touching. If you look at this thing itself, so these 2 loops are touching. You can figure that out. You can make that out, right?
3, 5.
Huh?
3, 5. Okay.
Right. We'll come to that. So we'll do 2 and 3. Are 2 and 3 touching? Minus G2, H2. minus G3H3. So this is not touching. Okay, so you have G2H2, G3H3. Okay. Are these two touching? G2H2 and G1H1. Yes, they are touching. So we are talking about this loop and this loop. Okay. Finally, this one and this one. Yes, they are touching again. Now let's do these two, G3H3 and G1H1. Again, these are not touching, right? G1H1 and G3H3. Okay. And if you look at these two, G3H3 and H2, these are also not touching. H2, G3, H3. Okay. Finally, these two, G1, H1 and H2. G1, H1, they are touching.
With that top loop, even though it's connected to the operator,
Mm-hmm.
you connect it to the 4S,
Mm-hmm.
V4S is connected to the signal,
Mm-hmm.
you would attach it to like that +1. That very top one, you see how it comes down no side.
V4.
But up there it isn't touching V4, that's the operator. Like a first chunk.
It's touching the summation block. So this summation, this is actually treated like a summation block. V4 goes into that summation block. Okay. So now you take 3 at a time. If you take 3 at a time, you do 1, 2, 3, 1, 2, 3, 1, 2, 3. Hmm? Say that again. So you take all the combinations. If you are given, see, if you are given 5, let's say 5 marbles, okay, and you're trying to figure out if there are similar looking marbles. So you're going to take 2 at a time. So 2 at a time, you're going to get 10 combinations. You're going to take 3 at a time, you're going to get 10 more combinations. You're going to do 4 at a time, you're going to get 5 combinations. We finished with this one.
I'm saying we went all the way to 5 because we had 5 loop games.
Right.
So no matter, so if we had 6 loop games, we would go 6.
Right. So if you had 6, you'll do 6C2, 6C3, 6C4, 6C5, and 6C6. Okay. So if you take now, let's do this. All right. So if you do these three are touching, right? At least one of them is touching. You looked at that. So if you do, because these two are touching. Okay. Now if you do these 3, 1, 2, 3, again they are touching because you see H1. So if you look at loop 1, it is G1, G2, H1 and G2, H2, right? So if these two are touching, so there is no point in combining these two with any of these. Okay, you can just forget about that. Now if you look at these 3, 1, 2, 3, again these are touching, right? You see G3, H3, G1, G2, G1, G2, and H1, G3, H3, and G1, H1. So the G1, H1 gets here. When you take 3 at a time, even if 2 are touching, you cannot take that as a non-touching loop gain. Okay? Is this getting complicated? Huh? So non-touching loop gains, the way you look at it is, non-touching loop gains taken 2 at a time, taken 3 at a time, taken 4 at a time, and taken 5 at a time. Huh? All right, let's just take a look at the definitions for these ones, okay? And we'll do a simpler problem. Is that okay? You understand non-touching loop gains? You might miss one. Yes, you might miss one. But it'll not be this complicated. At least the exam problem will not be this complicated. Okay, and you don't have to worry about this for midterm. Okay, so just understand this definition for now. Okay, non-touching loop gains. You get it mostly, and see it's become these loop gains. Of course, if you're doing a real-time control system, you will have to do a much more complicated system, right? But for exam, for assignments, these loop gains will mostly be 2 or 3. So your combinations are limited. Okay? So you have non-touching loop gains, and then so once you have figured this out, you use this definition Mason's rule is G of S or T of S is equal to C of S over R of S. It's summation of K over K, Tk delta K over delta. Okay, where K is number of forward paths Tk is the kth Okay. So you have, when you have something like this, once you have figured out these three elements, or these three, the loop gains, forward path gains, and non-touching loop gains, you can simply substitute these in this formula. It's called the Mason's rule, and you can figure out the transfer function. Okay. So here, what is, so let's look at one at a time. What is K for this example? 2. So number of forward paths, the number of forward paths here is 2. Okay. What is Tk, or what is T1? So you have this formula changes to, for this example, the formula changes to Cs over Rs is equal to T1 delta 1 plus T2 delta 2 over delta. Got it? So that summation of Tk delta K over K means this for this example. T1 delta 1 plus T2 delta 2, because K is equal to 2. Okay. So what is T1? T1 is the kth forward path gain. It is simply this G1, G2, G3. Got it? T1 is simply G1, G2, G3. T2 is G1, G3. That's it. All right. So delta, what is delta? Let's figure out delta first. So your delta would look something like this. So you have 1 minus, you add all of these. Got it? So you have whatever those are. G1, G2, H1 plus so on, all those loop gains, plus summation of non-touching loop gains. So you add all of these, taken 2 at a time. These are taken 2 at a time, right? So you have G1, G2, H1, G3, H3 plus so on. So the pattern here is, you have to pay attention to the pattern. It is 1 minus plus minus plus. So all the even combinations are plus, all the odd combinations are negative. You see that? So it is 1 minus plus. So this is just one loop, right? This is 2 loops or 2 combinations. This is 3. And for 4 it will be again positive. Huh? So you have delta, okay, delta is this, by definition this is the delta, okay. So you have minus loop gains. We have identified these loop gains, right? All you need to do is just add those loop gains, okay. And then you take non-touching loop gains taken 2 at a time, and you add those loop gains. Then you minus non-touching loop gains taken 3 at a time. So you subtract those loop gains when you take 3 at a time. Okay. And finally, delta K is delta minus loop gains that touch the kth forward path. So what you really need to do here is, so you look at the kth forward path, or the first forward path. The first forward path is this thing, right? Going right through. do you see any of the loops not touching the kth forward path or the first forward path? This is also touching, right? Yeah, if you look at RS to CS, any of the loops which are not touching, if all of them are touching, this would just be 1. Okay? Delta 1 would be 1. If all of them are touching, if you had something like this, so this is an example. And you have if you had something like this, then this loop is not touching the first forward path. But here, every loop is actually touching the forward path, both the forward paths. So it will just be everything, this will cancel out. So delta would be minus loop gains. So delta would be all of this. So if any of the loop gains are touching, you just keep cancelling those. So since everything is touching, only this one will remain. Okay, here delta 1 is 1 and delta 2 is also 1. Okay? Yeah. So it will be this plus this over delta. That would be your transfer function. No, delta is this. So you have delta is this. Delta k is either delta 1 or delta 2. Okay, based on the forward path. Delta is just delta. It's in the numerator. Think about this as when you have determinant, right? So this delta you will get at the bottom. So that is this delta. Okay. So delta 1 is a special case of delta, you can say. So when you do this, now look at that example and look at this. If you reduce that block diagram, you'll get something that complicated actually. If you just do block diagram reduction on that using cascade, you'll really get a complicated transfer function. So what you can do is, if you have something like this, you can just put it in the signal flow graph and get your transfer function. And you can design, in fact, you can design your own software which will give you the equivalent transfer function for signal flow graph. Okay. Any questions regarding the exam? Yeah, it's not. Yeah, it'll be mostly so that you can prepare for your. Do you want to submit that or not? I'm going to give you some examples.